Hello students, this is my first interaction as computer teacher of class 8. We have started this session in a new mode by conducting online classes to teach you people with the safety at your home. So I hope all of you are safe and healthy at your homes. In this class, we are going to discuss about the number system. Number system is the lesson 2 in your book, which is Computer Learning, written by Sumita Arora, and the publisher is Dhanpat Rai and Company. You people are already familiar with this topic, number system, as you people have studied this topic into your subject maths. But right now we are going to discuss the number system into the subject computer. Into this, we are going to see how the number is represented when we are going to store them into the computer. So first of all, what is the definition of the number system? The definition of the number system says that it is a way to represent a number. In digital representation, we use 4 types of the number system. First, decimal number system. Second, binary number system. Third, octal number system. And fourth, hexadecimal number system. To begin with, we are going to take the topic decimal number system. The decimal number system is the most commonly used number system. It is one of the earliest number system based on 10 symbols. 10 symbols which are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these 10 symbols make the numbers which are belonging into the decimal number system. The decimal number system is also called as the base 10 system. It is called as the base 10 system because it depends upon the 10 symbols which are making this all the numbers which are used into this number system. So the base of decimal number system is 10. For example, if we have to represent a number into the decimal number system, we just write the number using any of the digits which are used as the symbol of this number system. So let's pick up the number 4 and number 8. So if we are going to use the digit 4 and 8 to make a number 48, so if we have to represent this into the decimal number system, we are going to put a base which is suffixed at the right end. So this 10 means the base which is applied onto the number 48, and they together represent that this number 48 belongs to the decimal number system. In the same manner, we can represent the decimal numbers also. So suppose we are going to use the number 20.75. So this 2075, they belong to the symbols which are present into the decimal number system. They are all present into this number system. So 20.75 is used to make the number, and a 10 is written as the base to show that this number 25.75 belongs to the decimal number system. In the same manner, we can represent the numbers into the other number systems also. For example, next number system is the binary number system. Binary means 2. So into the binary number system, only 2 symbols are used, and they are 0 and 1. All the numbers which are used into the binary number system, they are made by the digits 0 and 1. No other digit is used to make the number which is used into the binary number system, or no other digits are used to represent a number in the binary number system. Whatever be the number, they will be the combination of 0 and 1 only. For example, if we have to represent 1, 1, 0, 1. Okay. So to tell that this 1, 1, 0, 1 belongs to the binary number system, we are again going to put the base 2 at the right end. So this base makes the difference that this 1101 belongs to the binary number system, but it does not belong to the decimal number system. So this base gives them the difference that to which particular number system the number belongs to, because 1101 can be the number which can be used into the decimal number system also, because 1101 or 101 are the valid symbols which are used into the decimal number system also. But to make the difference that this is the binary number system, not the decimal number system, this base gives them the difference. In the same manner, we use the other number systems also, like the octal. Octal means 8. So the 8 letters or 8 symbols belongs to the octal number system. They are 0, 1, 2, 3, 4, 5, 6 and 7. So octal number system has got 8 symbols, and all the numbers which belong to the octal number system are made by using these symbols only. So again, any of the number which we are going to write into the octal number system will be written by using these digits only. Suppose if we have taken the digit 3 and 4, but to make the difference that this 3, 4 belongs to the octal number system, not of the decimal number system, so we are going to put the base of 8 over here, because 3, 4 can be represented into the decimal number system also. So to give it a difference, we are going to use the base at the right end. The next number system is the hexadecimal number system. Hexadecimal, what does it mean? Hexadecimal means hexa as 6 and decimal as 10. So total 16 symbols are used into the hexadecimal number system, and these 16 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the letters A, B, C, D, E and F. So total 10 digits and 6 letters makes the hexadecimal number system. So the hexadecimal number system can have any of the values which belong into the hexadecimal number system. Means like if we have to represent a number into the hexadecimal number system, they are going to be written by using these symbols only. So suppose if we have used the letter A and we have used the letter number 2. So A2 is the number which is going to be represented into the hexadecimal number system. To give it a clarity, we are going to use the base 16 at the right end. So this 16 is going to tell that A2 belongs to the hexadecimal number system, not of any other number system. This is also the A gives it the clarity that A is only present into the hexadecimal but not in any other number system. But if we are only going to take the numbers, we are not working with the letters, then there might be the confusion, like if we have used the number 2, 3. So 2, 3 can be the number which can be used into the decimal also, it can be used into the octal also, and it can be used into the hexadecimal also. So if 2, 3 is represented into the decimal number system, we are going to put a base 10 over here. If we are going to represent this 23 into the octal, we are going to use the 8 over here. And if we are going to use the 23 into the hexadecimal number system, we are going to put the base 16 over here. This is explained into your book also with the number 100. Number 100 means that it can be a number which is going to be used, which can be used into the decimal number system also, or it can be used into the binary also, it can be used into the octal also, as well as it can be used into the hexadecimal also. So if we are going to use this 100, so the base is going to give it the clarity. 100 with base 10 represented into the decimal number system, 100 with base 2 represented with binary number system, 100 with base 8 represented with octal number system, and 100 with base 16 represented into the hexadecimal number system. So I hope you people got the idea what does the base mean. Base gives it the clarity that which number system a particular number belongs to. Secondly, this base is derived from the number of the symbols which are used into that particular number system. means 10 symbols are used into the decimal number system, 2 symbols are used into the binary number system, 8 symbols are used into the octal number system, and 16 symbols are used into the hexadecimal number system. The other name of the base is radix, means base is also known as radix. So we can say that the decimal has got the base of 10 or the radix of 10. The radix of binary is 2, the radix of octal is 8, and the radix of hexadecimal is 16. Next, we are going to move towards the positional value system. Positional value system. What is this positional value system is? Position. Every digit of the number has got some positional value. Means first of all we are going to take the example of the decimal number system only. Like the decimal number system is also called positional value system, which means that the value of each digit depends upon its position. Let's take the example of 573. 573 is the number which is written into the decimal number system. This 573 is made up of 3 digits 5, 7 and 3. Each digit, whether it is 5 or it is 7 or it is 3, has got the value at the particular position. The positional value that each digit has is according to their position where they are placed. Means 5, 7, 3. We are going to start from the right hand side. This right hand side digit is called as the LSD or the least significant digit. And from working from the right hand side, we move over to the left hand side, and the last digit at the left hand side is called as the MSD or the most significant digit. Means the digit which is placed at the right end has got the least significant value, and the digit which is placed at the left end has got the most significant value. So we are going to provide them the value. This positional value depends upon the base as well as their position. This 3 is represented into the decimal number system. So the base will be 10 and the positional value will be 0. This 7 will have the positional value as 1 and this 5 will have the positional value as 2. So we all know that any digit which has got the power of 0, its value is 1. So we say that 3 is at the 1's position, the 7 is at the 10's position and 5 is at the 100th position. So we all can see that the positional value of each digit keep on increasing. The least significant digit has got the 1's positional value, the second digit has got the 10th positional value and the third one has got the 100th positional value. The things would have been clear to you people. The same positional value is given to the digits which are used into the binary number system also. Here also, suppose as I told you people that any value into the binary number system will be written using only the zeros and 1. So suppose if we have taken a number 1, 1, 1, 0, 0. So this number 1, 1, 1, 0, 0 has got the 5 digits. So we are going to divide them into the 4 columns. One, 1, 1, 0, 0. Now we are going to provide them the positional value. As I told you people earlier, for the decimal number system we have used the base of the decimal, that was 10. In the same manner we are going to use the base of the binary, which is 2, to provide them the values. Again we are going to start from the least significant bit and move towards the most significant bit. So the least significant bit is at the right hand side, which is 0. So we are going to provide it the value of 2 to the power 0. The next digit will have the value of 2 to the power 1, the next one will have the value of 2 to the power 0, the next one will have the 2 to the power 3, and the most one will have the 2 to the power of 4. So in this manner we just keep on moving and providing them the positional values from the lowest significant bit to the most significant bit. Like in the same manner we can do it with the octal numbers also. Suppose if we have taken a number 371 as the octal. Okay, so this too will have the positional values 173, but here now we are going to use the base of 8 because 8 is the base for the octal number system. So 1 will have the 8 to the power 0, 71 will have the 8 to the power 1, and the 3 will have 8 to the power 2. In the same manner we can represent the numbers and providing them the positional value for the hexadecimal number systems also. Suppose if we have taken the number A to 5. So A to 5. The 5 will have the positional value of 16 to the power 0, 2 will have the value of 16 to the power 1, and A will have the 16 to the power 2. So all the number systems uses the positional value system also, which means providing them the positional value which depends upon the base as well as the position what they are holding. To give them the positional value, we start from the least significant bit or we start from the rightmost digit and move towards the leftmost digit. We keep on increasing the power onto the bases, and this power onto the bases provide them the positional value, which is also called as the weight for that particular number for weight for that particular digit. So I hope you people would have understand what is the base of the number system, how we are going to provide the positional values to the digits, as well as how many types of the number systems are used to represent the information into the digital manner. Now basically we are only going to work with two types of the conversions. They are the decimals and the binary. In this class we are going to see how to do the conversion of decimal numbers to the binary system, or how to convert the binary into the decimal number system. Okay, can you make a guess why do we want to convert the decimal into the binary? Yes, I thought I can make out the guess that you people are thinking the right thing, because from your early classes you have been taught that any information in the computer is represented in the form of 0 and 1. The computer does not understand what is 2 or what is 8 or what is 9. It only understands 0 and 1. So whatever the information is entered into the computer needs to be converted into the combination of 0 and 1. So if you are entering a number 48, this 48 needs to be converted back into the form of 0, 1. So how are we going to convert this number 48 into 0, 1? So converting 48 into the binary equivalent, we are going to use the process of repeated division. We are going to do the repeat division of the value or of the number by the base. So the base into which we have to convert it. So we have to convert it into the binary number system. So we are going to divide it with the base 2. Okay, how are we going to do it? Let's see how are we going to do it. So the process is to do the repeated division. So for the repeated division we are going to use the values For example, 48 is written over here. Now keep on dividing it by the 2 till the quotient becomes 0. So 2 will be divided by 48 will be divided by 2 So we are going to have the number 24 over here, and we are going to separate out the remainder. The remainder is 0. Again, this quotient 24 is going to be divided by the base 2. So this is the quotient and the remainder is 0. Again, this quotient 12 is going to be divided by the base 2, and we are going to have the base remainder as 0. Again, this 6 will be divided by base 2, and we are going to have the remainder as 0. This 3 will be divided by base 2, and we are going to have the remainder as 1. Now this 1 will be divided by 0, and we are going to have the remainder as 1. So as I told you all in the beginning, that for the conversion of decimal to the binary, we are going to do the repeated division by the base 2. So when we have done the division, when we have got the quotient, after getting the quotient, we have separated out the remainders. These remainders are only going to give us the actual figure, what is the binary equivalent of number 48. So to get the binary equivalent of number 48, we are going to accumulate all the remainders from bottom to top. From bottom to top. Do remember, we create the remainders from top to bottom, but we accumulate them from bottom to top. Means the first will be 1, the second one will be 1, and then will be 0, 0, 0 and 0. So this 1, 1, 0, 0, 0, 0 is the binary equivalent of the number 48 into the decimal. I hope you people would have understood it. So let's take the revision again. So what we have to do is that we have to divide a number with the base, and we have to separate out the remainders until the quotient becomes 0. Once the quotient becomes 0, we stop dividing further and we just accumulate all the remainders from bottom to top. And that accumulation of the remainders from bottom to top is going to give us the binary equivalent of the number which is represented into the decimal number system. I hope you people would have got it well. Now let's take a second example. Suppose if we have to find out the binary equivalent of number 13. So what we are going to do is that we are going to divide this 13 with the base 2. So first we are going to have the remainder as 1. Then we are going to have the remainder as 0. Then we are going to have the remainder as 1. And then we are going to have the remainder as 1. So the binary equivalent of number 13 will be accumulating from bottom to top 1, 1, 0 and 1. So this 1101 represents the binary equivalent for the number 13. So many more examples and many more values are given into your book. You people can do the practice by yourself and find out the binary equivalent of those numbers. You can take any number because you can make any numbers into the decimal number system using the combination of all the 9 digits and keep on dividing them with the base 2 till you get the quotient as 0 and then accumulate all the remainders from bottom to top to get the binary equivalent of that decimal number digit. Now on the other side, let's take the example how to convert this binary number into the decimal number system. Means the next we are going to discuss the conversion of binary to decimal. How are we going to convert the binary to decimal? For the conversion of binary to decimal, the positional values play the role. Now just suppose a number is 1, 1, 1, 1 into the binary. So this number 1, 1, 1, 1 into the binary will be represented with its positional values. So 1, 1, 1, 1. Now this is going to have the positional value of 0. This is going to have the positional value of 1. This is having the positional value of 2 and this is having the positional value of 3. What do we do is that we multiply the face values with the positional values. Means face values means what the digits are showing us. So here all the digits are showing us 1. So the 1 is called as the face values for these digits, and their positional value is, this is having the positional value of 0, 1, 2 and 3. So what we are going to do is multiply the face values with the positional values. So this is going to is having the face value as 1. So 1 will be multiplied with the positional value, means 2 to the power 3. This is going to be added with the second digit, which is having the face value as 1 and this positional value as 2. This is going to be added by the third digit, whose face value is 1 and the positional value is 2 to the power 1. And this is going to be added by the last digit, whose face value is 1 and the positional value is 2 to the power 0. Now simple mathematics will be applied over here. 2 to the power 3 is going to be 8, 1 into 8 plus 1 into 4 plus 1 into 2 plus 1 into 1. So 8 plus 4 plus 2 plus 1. This is equals to 15. So this 1111 into the binary number system is equivalent to number 15 into the decimal number system. So what we have done over here is that we have multiplied the face value with the positional values of every digit, and then we have done the addition of all the face values with the positional values, and the sum is the decimal equivalent of the binary numbers. I hope you people would have got it well. Let me explain you up with another example. Suppose if we have the number 10101. So what we have to do is that we have to provide the positional value to each digit 0, 1, 2, 3 and 4. So face value of the most significant bit is 1. 1 will be multiplied by the positional value 2 to the power 4, which will be added by the second face value, which is 0, multiplied by positional value 2 to the power 3, which will be added by the face value 1. Positional value is 2 to the power 2. The next digit has the face value of 0 and the positional value is 2 to the power 1, and the least significant bit is having the face value of 1 and the positional value is 2 to the power 0. Now let's do the mathematics. 2 to the power 4 is 16 plus anything multiplied to 0 will be 0 plus 4 plus 0 plus 1. So this is equals to 21 into the decimal number system. So this was all about the whole number system into your book, which is given into your book. So what we have, let's take up the revision. What we have discussed today was, we just discussed about the number system. The definition of the number system says that it is the way how we can represent any of the numbers. There are the 4 ways to represent the number system. One is the decimal number system, the binary number system, the octal number system and the hexadecimal number system. The decimal number system and the binary number system are the topics which we are going to deal into this lesson, whereas the octal and the hexadecimal too are there, but this is not into your course. We will discuss them later on. So all these 4 number systems are based on to the positional values, so they are also called as the positional value systems also. So positional value gives the weight to the numbers, and how the numbers are created, this we have already discussed earlier. And then we have seen how to convert the decimal into the binary and the binary into the decimal. To convert the decimal into the binary, we have to do the repeated division method, and to convert the binary into the decimal, we have to do the multiplication of the face value with the positional value, and we have to find out the sum of the products of the face value and positional value. So in this manner we are going to convert the binary number system into the decimal number system. So this was all for the today's class. I hope you people would have understood all the things what I have tried to explain you people. I have taken few examples to explain you people. You with the same process you people can work upon with the other numbers also and find out the values and find out the method how to convert the decimal into binary as well as the binary into decimal.